for the grand partition function, we find the mean number of particles for each state. Yes, that's like often what it's used for, because it's used for when you have a system that has fluctuating numbers of particles. So particles can come in and out of your system. So yeah, you're allowed to find, or it helps you find mean numbers of particles. In theory, you could make some other ensemble that allows flux of something else coming in and out. But yeah. So that isn't really the expression for finding the numbers of particles. I would have thought the expression is generally something like this, where you have your mean number of particles is equal to 1 on beta. What's a bad beta? D ln z of d mu, like that. Is that what you think? If you want to find the average number of particles in a particular state, and you have your partition function, and you differentiate with respect to the energy of that particular state, then because if you have non-interacting particles, then the partition functions of the states are a product of these, then you would have, because the logarithm of the product becomes the sum of the logarithms, so then you'd end up with only one term remaining, which is dlnzr der, because the rest would just be 0 because they're not differentiating with respect to er, that particular state. Does that make sense? I think I follow you now. Yeah, so it's just for non-interacting particles, because this expression wouldn't work if particles were interacting, I believe. Alright. Yeah. Sorry, I was confused slightly before about what you meant, because I didn't see the energy with respect to R, the rth state. Why does the rest go to 0? Because if you have your product of z of r, it's basically your partition functions are with respect to er. And so if you take the log of the product of these zr's, you end up with the sum of a bunch of logs of the partition function zr with respect to er. And if you differentiate this, so d of er, oh, that's bad. Let's label it el, because this product is not great. Hold on. Let's go m, 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 m. If you differentiate with respect to ER, then only one term will remain, because only one term is in terms of ER. I believe, is that what you're trying to say? Made this a bit of a mess. So if you just have yeah, I think that's I'm pretty sure that's how it works. That they're just independent states. So you're differentiating with the energy of that state, and so that's why you get the different partition functions that are separable, if I'm not mistaken. Yeah. Okay. So the question was about why, in the derivation of the canonical and grand canonical ensemble, do you take the logarithm of the number of accessible states and expand around the total energy? You don't expand around. It's kind of to make the numbers smaller, is the way that it's often said. And what you're really doing, because the log of the number of microstates, is you're expanding the entropy around its maximum. And so that's sort of why you get that term. So that's what you're really doing, but often what's stated before saying entropy is that. So as soon as you add more energy to your system, your number of states is going to increase exponentially, well, faster than exponentially. That's essentially what happens. Because you get more and more rearrangements, and it's going to be combinatorial, if anything, about how fast they will grow. And so that's why you take the number of the logarithm, because it makes the numbers more manageable. Yeah. I'll just have a look now. Something just quickly about the expanding the log. So we have from the microcanonical ensemble, right? You have your probability of your kth state is going to be equal to the degeneracy of the kth state over the total number of microstates. So we have that. Now, if we then go to the canonical ensemble, we have the probability of the kth state as a function of some total energy of the system, total energy of your environment plus system, and then the energy of your system itself. And what we then have as our degeneracy is how many ways we can split the energy over our system. So this is our microstates of our system for a given energy of our system, Nk, and the total number of microstates of our bath or reservoir, whatever you want to call it, which is the total energy of the system plus reservoir minus the energy of the system itself in the kth state over the total number of microstates, which is just the whole system. And so our degeneracy, in a way, is this, which is how many ways you can arrange the system to have the energy being partitioned into two separate bits. One is your system and one is your reservoir. And then you take, this is going to be some kind of constant for a particular energy. And so you just put a C out the front, and you've got your reservoir states. And then the reason why you take the log is that it's just more manageable. So you end up with E is the exp of log. Because then you can expand this and then it's slowly varying. That's essentially what they say often. Yeah. And so this isn't going to fluctuate a lot. So then you expand around that. Okay, so the next thing was question 3. So question 3 from the tutorial was about the dielectric function of a gas of dipoles. So we have a Hamiltonian, which has translational motion plus rotational minus some potential energy. And so we treat the dipole as classical rods, which means that our rotational partition function, our rotational kinetic energy is a half I theta dot squared plus phi dot squared sine squared theta. We know that from classical mechanics. And because all of the dipoles we assume, because it's dilute, we assume that there's no interactions between them. So that means that our total partition function is equal to the partition function for a single atom raised to the power of n, our number of particles. And our partition function, Zi, is going to have a few different bits. It's going to have our translational motion, our rotational motion, and our potential. And so, first thing we need to do is show that the rotational partition function is equal to something that's given in the Tute, and so let's just calculate that now. So, in our canonical coordinates, rotational Hamiltonian, I'm going to include the potential as part of the rotational part, the theta 2I plus p phi squared on 2I sine squared theta minus mu e cos theta. And then we just need to integrate our partition function, or our probability to find our partition function. So we've got our rotational is going to equal to, so this is our quantum correction factor, because we have two different coordinates, we have h squared. So we have our configuration variables, which is our angles, and we have minus our momenta as well, which can take on any value that it wants, and then our Boltzmann factor. And so now we can, because almost all, because some of these factors are separable, we can break them up into different bits. So firstly, let's start with the outermost one, or the innermost one, sorry, which is going to be e to the minus b p theta p phi gi sine squared theta dp phi. And knowing how Gaussian integrals work, which you should all now probably know how to do that for this course, because you're going to basically do mostly Gaussian integrals. Sorry, hold on. Two coordinates is at 3 and 5. Okay, so just a question, which was why two coordinates for the h squared there, and it's because it's coordinate pairs. If you have this correction factor is for how many canonically conjugate pairs of variables you have, which comes from basically how quantization works in a way, because you have your region of phase space, so your Q and P. It's basically giving you a correction for how small a specific region can be, and the smallest of that is h. Does that make sense? About why only h squared, not h to the 4? Alright, so I'm going to keep on going. Sorry. Alright, so this integral is going to evaluate to 2 pi I on beta sine theta. And so this is now going to track into the rest of our integral. And let me just start a new sketch. And so we also have dp theta e minus beta p theta squared on 2I, and this only has quantities relating to itself, so this is all good, and we can just say that is going to be 2 pi I beta. So we have this bit now, and we have one more bit, d phi. We have two more bits, but this is one before we get to the harder part. There is no potential term for d phi, so it's just we're just going to integrate that, and so we just end up with 2 pi. So let's put this all together now. So we've got z rotational is going to equal 1 on h squared, and we still have one more thing to integrate over. We've got d theta, 0 to pi. We have e to the minus or plus beta mu e cos theta. We have square root of 2 pi I on beta. We have another 2 pi. And we also have the 2 pi I on beta sine theta from the other integral. And so that is now going to come out as 4 pi squared on h squared beta times I. You could write that as a h bar squared if you'd like. Then 0 to pi e beta u e cos theta sine theta d theta. And you can then make a change variables. And let me just get to a new page. So we have after the integration, you get minus 1 on h bar 4 pi I beta squared mu e to the beta mu e cos theta pi 0. This comes out because when you differentiate e to the beta mu e cos theta with respect to d theta, you get beta mu e sine theta e to the beta mu e cos theta. And so you see the similarity there because you can just see that it's that's just dropping down and you can easily integrate it up. Okay, and so now that's going to end up with, we have minus 1 on h bar 4 pi squared I beta squared mu e to the minus beta mu e minus e to the beta mu e. Just substituting in those numbers, and we then end up with 8 pi squared I on h bar beta squared mu e sine of beta mu e. So that's what we end up with. So that's that bit. If you're still unsure about this integration as well, you can do a change of variables where x is equal to cos theta, and then you have dx is equal to sine theta d theta, and then you just substitute it in and integrate. It's not too hard. Alright, so the next part of this question is looking at the polarization. And so the polarization is given by N0, which is our number density, mu cos theta. And we need to show that it's equal to N0 mu cos beta mu e minus kt on e. Alright, cool. So we have this equation for the polarization. So we can now do it in terms of probabilities and averages. And we get N0 mu naught, and now we find the average. So we've got 2 pi. That's a 2 pi. Sorry. Pi 0 cos theta e to beta mu e cos theta sine theta d theta over the normalization beta mu e cos theta sine theta d theta. Alright, so that's basically back to where we were when we were halfway through finding the partition function. I've integrated over every other variable but d theta. And from this, we notice that if we differentiate the partition function, so if we differentiate this here, so we've got some stuff out the front, e beta mu e cos theta sine theta d theta. If we differentiate this with respect to the electric field that's been applied, then what we end up with is beta mu cos theta, bring that inside, C there, e to the beta mu e cos theta sine theta, which is what's at the top. So what we can now write is that our polarization, which is n naught mu cos theta, is going to be equal to n naught on beta differentiate, oh, hold on. One on z, our partition function, our rotational partition function, d of dE of our partition function. And that is then equal to n naught beta d dE log of our partition function. And basically we can do the log of the whole partition function, but that's not necessary. And so if we evaluate this now, we have n naught beta of this mess. So we have dE log ln 1 on h bar 8 pi squared I beta squared mu e, and then shine beta mu e. And if we break the log into 2 bits, so we have n naught beta dE of log of some stuff, let's just call it C, minus log of E, and then plus log of sine beta mu e, and then we differentiate these bits. What we end up with is what we wanted at the beginning. So we have polarization is going to equal n naught mu outside of coth of beta mu e minus mu minus 1. Coth comes from the fact that you are differentiating this expression sine of mu beta e. You're differentiating this expression, which you can then write as 1 on shine mu beta e, and then d dE of shine mu beta e, which is a coth, which is a cosh, sorry, which gives you a coth. Hey, so it looks like we can. Okay, so there was a question which was that it looks like I calculated the average of cos theta, and you're wondering over what. So let's go back to the average. So we have P is equal to mu n mu cos theta. What I'm really taking an average over is everything. So I have 0 pi, 0 to 2 pi, minus infinity to infinity, minus infinity to infinity of all of our variables. D P of theta, D P of phi, and over cos theta, e to the minus beta h and then over z. But what I've done is I've just skipped ahead a few steps because I already know that from what we calculated earlier to calculate z, our partition function, I got to a point where I just had the integral of d theta there, which was our integral, like so. Which was that. And I just got us straight to that point instead of having to go through that integral again. Does that make sense? Does anyone else have any other questions as well from the tutorial or from anything else? Okay. There was a question which was, so is the partition function kind of a probability distribution? It's not. It's the normalization for the probability distribution, essentially. That's it. It's a silly name that has a weird historical reason why it's called that, but it's the German name for it translates to sum over states, which is what you're doing. So it's like you're finding your total number of states for continuous systems and for non-continuous systems, really, I guess. And it's also the canonical and grand canonical version of your total number of states, your total number of microstates, essentially. So it's the normalization for your probability. Does that clear things up? Yeah. So this is why the partition function only has, it doesn't have any of your like motional degrees of freedom, like momentum or your like position and stuff like that, because it's summed over them. What do you mean? There was a question that said, why do you integrate over it? What have I integrated over? Okay. So, if you were doing any old average, right? Let's say I wanted to find the average of x, and I have some probability distribution, and it's over x, so it's over some sort of region, x, p, x, dx, right? So that's just the general like formula for an average. And oops, there we go. All right, so you've got some this is your general form for an average here, and if we substitute in, say, our x in our situation, which would be cos theta, and our probability distribution for cos theta in this situation is going to be e to the minus beta of our Hamiltonian, which is going to be a function of theta or cos theta, over our partition function, because that's our normalization there. Otherwise, this thing up here is going to be unnormalized. Does that make sense? So you'd have cos theta and all the other bits. All right. Do you understand now what I'm saying? And that Z goes out the front. Maybe also I should clear this up here. Does that make sense? Or I'm not sure. Maybe I just thinking that for a while. It's also like, because this is a marginal probability distribution. I don't know if you've really encountered them yet, but it's kind of like if you have a probability distribution of two variables, let's say, and you only want a probability distribution of one variable, what you need to do is you need to integrate over that other variable, right? And so to get the probability distribution of P of theta, then we need to integrate over the other three variables, e to the minus beta h of theta, phi, p theta, p phi, z. Is this where the confusion was coming from? I only wrote out z as well in a long form just to show the similarities between the average of cos theta and the just finding the partition function itself. Because the other thing is, well, the partition function acts as a way of generating something called cumulants, which is sort of like the moments of your system. So like averages and standard deviations and anything higher than that are just calculated from this because of how it's how it normalizes it. So it acts as that as well, because of the form of the probability. All right. Okay. Well, if there's, I can do one more question if someone wants to answer one. If not, I think we'll sign off. I'll upload some work solutions, I think, to the rest of them as well at some stage, videoed. But yeah, other than that, if there's any other last questions.
Alright, we might as well sign off then. And if anyone has any questions during the week, just email me on my normal email. Everyone has the schedule as well now, I guess, from online. So yeah, it'll be just those dates and times from now on. Because I just moved it forward by an hour because it was just just a bit of a better timing. So yeah, thanks everyone. I'll see you next week.